All right. So let's talk about a derivative kind of in its most basic form. So let's say we have our xy axis. And let's say we have something that does this. Okay? Now, I'm not too worried about what it looks like. But what happens is, what a derivative finds us is it basically lowers the dimension, and it finds you like an equation that you can find out exact values of where lines that are tangent. Okay, so let me use a nice pink line. Who did? All right. So let's take us back to geometry. And I'm going to say the pink line is tangent to the red line, or the red graph. Okay? So if you remember, there was you've heard of the word tangent used in geometry, but then you might have known the word tangent maybe from like middle school. Something that is tangent to something else is something that touches something once. Okay? So a tangent is a line that touches, tangent line touches one time. Okay? Does that seem to be verbiage that you'd be okay with? All right. So other things that we know is we would know that we have an x value down here. And if that x value, we came up and then came over, we could then find a y value. But there's just some things that tangent does. Okay? So just for right now, take away, you remember you had sine, cosine, tangent back in geometry. Sine was opposite over hypotenuse, and cosine was adjacent over hypotenuse, and tangent was opposite over adjacent. And your teacher might have taught you SOHCAHTOA, but I don't do SOHCAHTOA because it's disrespectful to the Native Americans. I do SOHCAHTOA as SOHCAH. You all might not have heard this one before, but this is basically, the thing they say, hey, this is how you remember it. Well, I don't discredit or want to say anything bad about the Native Americans, so I make fun of the hippies. Is that okay? Ready? Follow my thought. Some old hippie caught another hippie tripping on acid. Okay? I think that's a nicer way to think about it. If you make fun of the hippies, they're too stoned to realize you're making fun of them. But like, dude, my dad's a hippie. I'm sorry, made fun of your dad. So this is one spot that you saw tangent in the relationship of right triangles. And then there's the tangent line. The tangent line and the tangent of opposite over adjacent, they are indeed related if you were to draw the triangles in place. But we're not there. We're just trying to realize that a tangent line is a line that touches one time. Okay? And the key here is a line. So let's go back to Algebra 1 a little bit. We've all seen this equation. Okay? You might have seen this equation. You might even seen this equation. These are all different ways that we could represent a straight line as an equation. y equals mx plus b. B is the y-intercept. M is the slope. You have point slope where you take the opposite values of x1, y1 to find you a point. Then you use the slope to find a second point. And then ax plus by equals c. You might remember something called the cover method as a way of graphing that. And that finds you basically the x and the y intercepts in order to graph it. Okay, they're all related. They're all can be the exact same thing. Yes, you can convert between all of them, but it's not the most fun. But so let's just kind of jump into, I wanted to take the derivative of a constant. Well, we have to remember that a constant is just a number. So you represent a derivative by going d over dx. And if I wanted d over dx of a number, let's say 55, the derivative of that is just 0. Okay? So any number, if it's just a number with no letters attached, then the derivative is 0. Okay? Just go to it. Whatever number you want. 5, 20, 66, 254. Doesn't matter. The derivative of just a number is 0. Okay? Seem good so far? Not too impossible. Now, I'm going to give you just the examples they have. They want this, 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 and this. And we want d dx over each. That just means we're taking the derivative. All right. This is to the first power. Agree? This, if in order to take the derivative, I'm going to show you the longer way. Yes, you can do the shortcut here in a second. I just want to show you the longer way. So you bring a 1 out front, and then you get x, and then you get 1 minus 1, which is 1 times x to the 0. You realize x to the 0 is 1, so you just get 1. This one's going to become 2x, and then you go 2 minus 1, so you get 2x to the first. This one should have been x to the third, and then this is x to the n. This one here is going to become 3x, 3 to the 1, x minus 1, or 3 minus 1, which becomes 3x to the second. So then if I do the derivative of this case, I get n times x raised to the n minus 1. Okay, so these are all ways to take a derivative. Okay, and yes, you can get equations, and we'll start exploring it. There's certain numbers that'll work for equations that are just fine. But we'll just learn the rules as we progress along. This is basically called the power rule. The power rule just exists if you don't have any square roots, you don't have any letters in the denominator, you just take whatever the exponent was, you bring it down to the front, and you go from there. Can I move off there, or is anyone still copying? Good in the hood? All right. So let's say we had 10x to the fourth power. Now I want to take the derivative of this. So I'm going to go 10 times 4, x, 4 minus 1. So this gives me 40x to the third. Okay? So that's how that derivative takes place. Notice the 10 stayed as is. I just kind of ignore it. I do the derivative with respect to x. That's why dx is on the bottom. It means you're doing the derivative with respect to x. Okay? Yep. Yep, just ignore it. All right, so let's have you all try these. ddx, not equals. Okay, see if you can figure those out on your own, if you don't mind. Oh, I got stuck in my chair. It's my own fault. I circled each of the answers. Do you agree? Do I need to have 38x raised to the first power, or do you think I can just have 38x? Yep. So that's the first part of a derivative. Now, again, there's a little bit more meat and potatoes that come along with some of the derivatives, but for the most part, these are just quite simple. Bring down whatever the highest exponent is, multiply it times the base, reduce the exponent by a factor of 1. Okay, and the reason why this one works is x raised to the 0 is equal to 1. So this is technically 4 times 1, which is just 4. A-okay? Anyone else need any more time? All good? All social media is good? Good. How does he know? No. All right. So let's look at the sum rule and the difference rule. This is on the back side of that page. Not real hard to do. So let's say I want to do dx of 3x squared plus 5x plus 2. I'll just go with product. What's the derivative of 3x squared? 6x. That's to the first, and that's plus 5. So let's do one that's a little bit more in depth. So what's the derivative of 10x to the 5th? 50x to the 4th. What's the derivative, and I have a plus sign, what's the derivative of 3x squared? What's the derivative of 2x? And then the derivative of this would just give me a 0. Friends, you're finding derivatives. Yeehaw. You had no idea it was such cool stuff. All right, and then the difference rule is just the same idea, but if we had subtraction signs. So if you had subtraction signs in there, derivative of this is 12x to the second minus 4x to the first minus 3. There's your derivative. Do what? Because in like full-blown real person calculus, there would probably be things that would change around with it a little bit. But we're just doing this simplistic. Okay? All right. So what would you think we should do if I wanted to find d dx of 3 over x to the fourth plus 7 over x to the third plus square root of x plus the third root of x squared. Okay? So things have to move and things have to come out of being radicals. So the first thing you're going to do on this problem, before you do any derivatives, is realize I could do 3x to the negative 4 plus 7x to the negative 3 plus x to the 1/2 power plus x to the 2/3 power. So it's a matter of realizing how I convert denominators to bring them up, radicals to become certain x or certain fractional powers. You go from there. All right. This is going to give me negative 12x minus 4 minus 1, which gives me negative 12x to the minus 5. The next one gives me minus 21x to the negative 3 minus 1, which is negative 21x to the negative 4. Then I have this one. This is going to give me plus 1/2 x. And then I'm going to go 1/2 minus 1, which is going to give me 1/2 x. Change that to 2 over 2 to the negative 1/2 power. And then the last one, I'm going to go plus 2/3 x to the 2/3 minus 1. There's a minus 1 right there, trying to be. Plus 2/3 x, x to the negative 1/3. Okay. That's the derivative of the whole red. Okay. Now, friends, I am not worried about you cleaning up derivatives so you don't have negative exponents and things like that. In Stirrups class, you get to leave derivatives dirty. And that's totally 100% fine with me. Okay? You got all next school year to figure out how to clean them up. But I just want you to have doing the derivative down. Okay. So can I move off here? Somebody's having a good old time. All right. So let's go back and take a look at this kind of graph. We have directional changes at certain locations. All right. All along here where it's increasing is positive. It gets to this green dot, it's 0. Then here it's all negative. Gets to this green 0. And then it's all positive. And then it's 0, and then all negative, and then 0, and then all positive. Okay? So the positive, negative, and 0 refer to the slope of the tangent line. Okay? All that really means is this. Let's pick a color that people will say, don't ever do that again. Let's see, change you. How about the color of yuck yuck? Let's change that color. These gross colors are tangent lines. Those all have a positive slope. As I come down, these have a negative slope. As these come up, these have a positive slope, and they do flip-flop on either side of the line, which we'll talk about as points of inflection in a little bit. But the positive and negatives refer to what's taking place there. At the zeros, I would have a slope of each of these lines being 0. That's all it means. And we'll eventually get to creating something called sine lines on how these things take place. Okay, so let's see. I think I might have done enough damage to this point. Yeah. Oh, and then one last thing I want to show real quick. So let's say I had this kind of graph. Let's just do a parabola. And let's say this is y equals negative x squared. And I wanted to find the instantaneous slope at that point. Okay, so let's say I have my xy axis drawn in place. Kind of looks like that. And let's say this is the value of negative 3. So I'm going to go dy, or d over dx of negative x squared, which gives me negative 2x to the first. And I want to find the instantaneous velocity, or the instantaneous rate of change. Change at negative 3. So all I'm going to do is I'm going to take this negative 3. Once I do the derivative, I'm going to plug it in. The instantaneous rate of change is negative 2 times negative 3, which is 6. So that becomes my slope of that particular red tangent line at that point. Okay? All right. I think you could do worksheet. Let's start on it. Worksheet 4.3. And I bet you can do 1 through 7. I'll give you the rest of the period to work on it and go from there. Cool? I'll stop recording there.